In this video, we will discuss entropy. What is entropy? Well, simply put, entropy is chaos. But a more useful definition is that entropy is a measure of how spread out or dispersed a system's energy is. To understand what entropy is and how we can use it in thermodynamics, it is important to understand entropy in the context of thermochemistry. Take, for example, the dissolution of cesium hydroxide in water. This reaction is exothermic, generating about 60 kilojoules per mole, and it is spontaneous. It does occur. Why does it occur spontaneously? Well, the release of heat energy is a driving force for this reaction. Solid cesium hydroxide possesses a considerable amount of potential chemical energy as compared to aqueous cesium ions and hydroxide ions. Compare this to the dissolution of potassium nitrate on the right. This reaction is endothermic and requires about 35 kilojoules per mole. There's actually less potential energy in the reactant as compared to the products. But the reaction is still spontaneous. Why is that? In this case, at room temperature, the transfer of heat energy is not a driving force for the reaction to proceed. There must be some other driving force or energy at work for reactions such as this. That energy is entropy. Now we can quantify entropy, S, as the natural log of the number of possible microstates of a system times the Boltzmann's constant. But this goes beyond the scope of this video. What we are really interested in is quantitatively measuring the entropy change of a chemical reaction and relating that to the spontaneity of the reaction, whether or not it will proceed. But first, let's take a little qualitative view of entropy, simply based on the amount of disorder of matter. By this definition, we can conclude that the entropy of a gas is greater than that of a liquid, and the entropy of a liquid is greater than that of a solid. The entropy of a solution is greater than that of the individual components alone. The entropy of complex molecules is greater than that of simple molecules and atoms, simply based on how many orientations they can take. Increasing the temperature, and therefore molecular movement, of a substance will increase its entropy. And in general, a reaction that increases the number of moles of gas will also increase entropy, and vice versa. So how do we measure entropy? Well, we don't possess an instrument that can measure the inherent entropy of a substance, but using the second law of thermodynamics, we can relate the change in entropy of a system with the heat gained or lost by the system using the following equation. The entropy of a substance can be obtained by measuring the heat required to raise the temperature of a given amount using a reversible process. Reversible heating requires very slow and very small increases in heat. Which brings us to standard entropies. If you recall Hess's law from thermochemistry, we can use the standard enthalpies of formation of reactants and products in order to calculate the approximate enthalpy of a reaction. This value tells you how much heat energy is released or absorbed by the reaction. The same tables at the end of every chemistry book also include standard entropies of various compounds, elements, and ions. By subtracting the standard entropies of reactants, times their stoichiometric coefficients, from those of the products, we can calculate the standard entropy change of a reaction. The caveat here is this only applies to reactions at 1 atmosphere of pressure, 1 mole per liter of concentration, and at 25 degrees Celsius. Under any other conditions, these values should be considered estimations. It is also worth noting that the units of standard entropy are joules per Kelvin per mole, as opposed to the usual kilojoules per mole associated with standard enthalpy. So a quick review of using the standard entropy information in the back of any textbook. We're going to take the reaction of hydrogen bromide with oxygen to create bromine and water. Again, this is products minus reactants, and always multiply these values times the stoichiometric coefficients in your reaction. So for instance, we have 2 bromine molecules. Make sure you get the correct state of matter. Add to that the 2 water molecules, liquid, not gaseous form, and not hydrogen peroxide. we're going to take the sum of those entropies and subtract from that 4 hydrogen bromide molecules in the gaseous phase and 1 oxygen molecule. Here we have an entropy change of negative 554.52 joules per Kelvin per mole. So what can we do with these standard entropies of reaction? Well, according to the second law of thermodynamics, if we add the entropy change of our system, or reaction, and the entropy change of our surroundings, we get the entropy change of the entire universe. If the entropy of the universe is increased, then the reaction was spontaneous, and it will proceed as written. If the entropy of the universe decreases, then the reaction is not spontaneous. It will not occur under those conditions. And if the sum of the entropy of the system and the surroundings is 0, that means your reaction is at equilibrium. Well, we know that what the entropy change of the system is. That's the entropy change of the reaction, which we just calculated from the standard entropies found in the back of the book. But how do we find the entropy change of the surroundings? For the entropy change of the surroundings, we need to use this equation. We need to know the enthalpy of the reaction and the temperature at which the reaction was performed, which in this case we're going to assume is room temperature, 25 degrees Celsius, or 298.15 Kelvin. So we have a lot of calculations to perform here. Let's use our hydrogen bromide oxygen reaction as an example. Now we already calculated the entropy of this reaction. Now we need to go back and calculate the enthalpy of the reaction in order to determine what the entropy of the surroundings were. So just as we did before, we're going to take the column that includes the enthalpies of formation. We're going to take the enthalpies of formation of the products minus the enthalpies of formation of the reactants. That's going to give us our answer in kilojoules per mole. We're going to plug that in to calculate the entropy of the surroundings. And before we can use this value, we're going to have to convert it to joules per Kelvin per mole to match the entropy of the reaction. Now we add the entropies of the reaction and the entropies of the surrounding, and this gives us a value. Now the actual value is unimportant, but what's important is that this value is greater than 0. So if it's positive, that means the reaction is spontaneous and it will occur as written.